Now we are ready to discuss an algorithm that computes the dominance frontiers of all the nodes in the graph. So before I do that, I want to recap this concept of a control flow graph, which we are already familiar with of a program, and a dominator tree. Recall that a dominator tree, so for example, the dominator tree shown on the right is the dominator tree for the control flow graph on the left. And the idea is that some node X in the dominator tree dominates another node Y in this tree if and only if there exists a path from X to Y. So for example, in this tree, A dominates itself, A dominates C, A dominates pretty much everybody. C dominates E, but C does not dominate, let's say, B or D, because there's no path from C to B or C to D. So that's the idea of a dominator tree. And in fact, more precisely, basically we have this relationship called the immediate dominator. Recall we had discussed this when we had introduced the notion of domination. And you draw an edge between two nodes if B is immediately dominated by A, or A immediately dominates B. Immediately domination relation, or IDOM relation, basically says that A dominates B, but A is not equal to B, so it's not a reflexive relation, and there exists no other node C such that A dominates C and C dominates B. So for example, A dominates D, but A does not immediately dominate D, because there exists a node B in the middle which is dominated by A and which dominates D. And so the immediate dominator relation is basically the immediate form of the dominator relation. And because the immediate dominator is unique, we can also represent this relation as a function where for every node we say what is its immediate dominator. For example, the immediate dominator of D is B. The immediate dominator of C is A. The immediate dominator of B is also A, and so on. So basically the immediate dominator of a node is the parent node in the dominator tree. So IDOM D is B, IDOM F is A, IDOM B is A, and so on. And we can represent this IDOM as a function from nodes to nodes. So given a dominator tree, or I'm also going to call it an IDOM tree or immediate dominator tree, some properties simply fall out from this tree representation of the immediate dominator function. If X dominates Y, so which means that there exists a path from X to Y in the dominator tree, then IDOM of X also dominates Y, because IDOM is the ancestor of X or the parent of X. So if there's a path from X to Y, then there's a path from the parent of X to Y as well. Similarly, if X strictly dominates Y, which means X dominates Y but X is not equal to Y, once again that basically means that there's a path from X to Y, and we discard the epsilon path, the empty path. We don't consider X to strictly dominate itself. Then IDOM of X also strictly dominates Y, because there is a non-empty path from IDOM of X to Y as well in the dominator tree. So some examples. So I guess there's no need for examples there, but I want to say something more here. So if X does not dominate Y, then we can't be sure whether IDOM X dominates Y or does not dominate Y, etc. For example, C does not dominate F. C does not dominate F, but C's parent, which is IDOM A, IDOM of C, which is A, dominates F. But if I take another example, E does not dominate F either, but E's parent also does not dominate F. So it's not necessary that if X does not dominate Y, then IDOM X does not dominate Y or definitely dominates Y. It depends on, it depends on the tree, and it may or may not dominate. And that's why I show this as a question mark. Similarly, if X does not strictly dominate Y, then IDOM of X also we cannot find a relationship between IDOM of X and Y in terms of whether it strictly dominates Y or not. Once again, E does not strictly dominate F, and C does not, the parent of E, which is C, does not strictly dominate F either. But if I look at C, then C does not strictly dominate F, but the parent of C, which is A, strictly dominates F. So we have examples of both kinds in this example. Now, I'm interested in computing the dominance frontier of a node X. And here is a naive algorithm to do this. The naive algorithm takes every node X one by one and tries to compute the dominance frontier of that node. So for example, let's say I take the node X. I simply perform some kind of a depth first search traversal on the control flow graph starting at X, because I'm interested in exploring all the paths. And on all the paths, I stop at any node that is not strictly dominated by X. And that I put in the dominance frontier. Recall that that was the definition of dominance frontier. Basically, on the path, all the nodes on the path are dominated by X, except for this node which is not strictly dominated by X, in which case I just put it in my dominance frontier and stop there. So to compute the dominance frontier of X, I perform a depth first search on this control flow graph starting at X and stop at any node during that depth first search that is not strictly dominated by X, and that node on which I stop, I put it in the result, which is the dominance frontier of X. And I do this for every node X. Now, what is the running time of this naive algorithm? Well, I need to look at every node separately. And for each node, I have to do a linear amount of work, which is either linear in the number of edges or the number of nodes, whatever is the maximum. And so linear amount of work for every node, and there are a linear number of nodes, which is n number of nodes. So then that's quadratic running time. Now it's clear that this naive algorithm has a lot of repeated work. For example, if I'm computing the dominance frontier of X, then maybe that has some relation to the dominance frontier of the parent of X. When I say parent, I mean the immediate dominator of X. And so I'm not using that information at all. I'm recomputing the dominance frontier for every node from scratch. And because I'm interested in computing the dominance frontier of all nodes, I can perhaps do better. And that's what I'm going to discuss in this module. So first of all, I want to point out that if a node Y belongs to the dominance frontier of X, then it's not clear whether Y also belongs to the dominance frontier of the parent of X or the immediate dominator of X. So for example, in this example, B belongs to the dominance frontier of B, right? We have seen this before. But the B does not belong to the dominance frontier of the parent, dominance frontier of the parent of B, which is A. So B does not belong to the dominance frontier of A, but B belongs to the dominance frontier of B. Whereas if I look at D, then B belongs to the dominant frontier of D, but B also belongs to the dominance frontier of B. So, I'm not I cannot say for sure. It depends on the structure of the control flow graph and on the dominator tree to be able to say that, whether if Y belongs to the dominance frontier of X, then is it true whether it still belongs to the dominance frontier of the parent or the immediate dominator of X. So example, F belongs to the dominance frontier of B, but F does not belong to the dominance frontier of A. So here's one more thing that I want to bring out, which is that if Y belongs to the dominance frontier of X, then it's not necessary that Y also belongs to the dominance frontier of I dom X. It's also not, it may or may not. So for example, F belongs to the dominance frontier of B, but F does not belong to the dominance frontier of A, because A's dominance frontier, recall, is empty because A pretty much strictly dominates everything. But on the other hand, F belongs to the dominance frontier of D, yet F belongs to the dominance frontier of B, where B is the parent of D or the immediate dominator of B. So if Y belongs to the dominance frontier of X, Y may or may not belong to the dominance frontier of I dom X. So I'm going to define a couple more terms or relations, and to basically move on to my actual algorithm to compute the dominance frontiers efficiently. So domF up for a given node X is all the set of nodes Y such that Y belongs to the dominance frontier of X and Y belongs to the dominance frontier of the parent of X or the immediate dominator of X. In other words, domF up X are the nodes in domF X, in the dominance frontier of X, that are passed up to the parent of X, to the dominance frontier of I dom X. And this will be helpful in doing the dominance frontier computation for all the nodes. Recall that our naive algorithm had this wasteful computation where the dominance frontier of the child nodes were not being used in computing the dominance frontier of the parent nodes. But this quantity here, this relation here, domf up, will help us do that. So domf up are the nodes in domf x that are passed up to the domf of the parent of x. Okay, so in other words, this is the set of all nodes y such that y belongs to the dominance frontier of x, and the immediate dominator of x does not strictly dominate y. Now, I'm saying that these two sets, the set that I've written in gray here and the set that I've written in orange here, they are the same things. Y belongs to dominance frontier of x is common in both the sets. The only difference is that here I'm checking whether the immediate dominator of x strictly dominates y or not. And I'm saying that, well, immediate dominator of x will strictly dominate y if and only if y does not belong to the dominance frontier of idom x. In other words, if immediate dominator of x does not strictly dominate y, then y belongs to the dominance frontier of idom x. And it's easy to see that because if y belongs to the dominance frontier of x, then there is some predecessor p of y that is dominated by x. And if something is dominated by x, then it must be dominated by idom x as well. And so there is some predecessor p of y that is dominated by idom x. And if idom x does not strictly dominate y, then we know that y must belong to the dominance frontier of idom x, which is what we wanted here. Right? And you can do the other side of this equivalence as well. And so the dominance frontier, the domf up of x, is basically all the nodes that belong to the dominance frontier of x, and they are not strictly dominated by the parent of x or the immediate dominator of x. And so this is pretty easy to check. Once I have the dominance frontier of x, all I need to do is I need to check which of these nodes are strictly dominated by idom x, and if a node is not strictly dominated by idom x, then it is surely in the dominance frontier of idom x. And this is a key idea that I'm going to use to be able to pass on the information of the dominance frontier of one node to the dominance frontier of its parent. So for example, the dominance frontier up of E, which is this node, is G. So what is the parent of E? It's C. And what is the dominance frontier of E? Well, dominance frontier of E was E and G, but E is not strictly dominated by C. E is strictly dominated by C, so E is not in the dominance frontier of C, but G is not strictly dominated by C, so G is in the dominance frontier of C, and so domf up of E is G. So how did I figure this out? Well, I mean, once again, domf of E is E comma G. Now I want to check which of these is strictly dominated by the parent of E, which is C. So E is strictly dominated by the parent of E, which is C. So E is strictly dominated by C, and so E does not appear here. But G is not strictly dominated by C, so G appears here. Okay, let's take another example. Dominance frontier, domf up of D. Domf up of D is all the nodes that are in the dominance frontier of D. Recall that the dominance frontier of D was F, G, and B. So F, G, and B. And of these, all the three nodes actually are also in the dominance frontier of the parent of D, which is B. So all the three nodes are actually passed up to the parent's dominance frontier because all the three nodes are not strictly dominated by B. Neither is F strictly dominated by B, nor is G, nor is B. B is dominated by B, but B is not strictly dominated by B. Okay. Okay, so that was one relation that I defined. This is domf up. Similarly, I'm going to define another relation called domf local. Domf local is all the nodes that are in the dominance frontier of X, and they are in the immediate successors of X in the control flow graph. So domf local X are the nodes in the domf X that are the immediate successors of X in the control flow graph. So by immediate outgoing edges, which of those are in my dominance frontier. In other words, when will a node be in the dominance frontier, an outgoing edge to PC be in the dominance frontier? If I don't strictly dominate it. If I strictly dominate it, then it cannot be in this dominance frontier. But if I don't strictly dominate it, then I dominate its predecessor, which is myself, because domination is a reflexive relation. So that would mean that it is in the dominance frontier of that DOMF local of node X. So in other words, Y is in the DOMF local of node X if X does not strictly dominate Y and Y is a successor of X. And you can check for yourself that these two relations are equivalent. As I said earlier, if Y is in the successor set of X, which is the common thing here, and X does not strictly dominate Y, then I know that Y must be in the DOMF of X, because after all, a predecessor of Y is X, and X dominates X, so it satisfies the DOMF condition. And you can also check the other side of this equivalence. So this is also very helpful, because if I want to check what are my immediate successors, which of my immediate successors are in my dominance frontier, I only need to check which of them I strictly dominate. The ones that I don't strictly dominate are in my dominance frontier, and that forms my DOMF local set. So here are some examples. The DOMF local of B is the empty set. So notice that the immediate successor of B is only D. That's the only successor. And D is strictly dominated by B. So DOMF local of B is just the empty set. Recall that the DOMF of B is actually made up of 3 nodes, which is B, F, and G. But when I say DOMF local, I'm only interested in the immediate successor, and there's only one candidate in immediate successor, which is D, and D is not strictly dominant. D is not in the dominance frontier of B, hence it is not in the DOMF local of B. Said differently, D is not strictly dominated by B, and hence it is not in DOMF. D is strictly dominated by B, and hence it is not in the DOMF local of B. Similarly, if I look at DOMF local of D, then B, F, and G are the immediate successors, and all 3 of them are also in the dominance frontier of D, and all 3 of them are also not strictly dominated by D, and hence all of them are part of the DOMF local of D. Similarly, DOMF local of E is E and G. These are both of them are successors, and they are both also part of the dominance frontier of E. Okay, so here's our final interesting property that we are going to use to compute the dominance frontier efficiently for all the nodes. The dominance frontier of any node X is formed by the local DOMF, which is the DOMF of from the immediate successors of X, and unioned with the DOMF up of all the successors Z, of all the children of Z in the dominator tree. So when I say children, I mean in the dominator tree. When I say successor, I mean in the control flow graph. So if I look at all the children of X, and let's say one of those children is Z, then I look at the DOMF up of Z and take the union of all of them, and then take that union with DOMF local, and all this will basically constitute my DOMF X. To see why this is true, let's take a few examples. So DOMF A is the empty set, because its immediate set, the DOMF local is basically, look at the immediate successors, which are B and C, and both of them are not in the dominance frontier of A, because both of them are strictly dominated by A. So that becomes the empty set. So DOMF local of A is just the empty set. And then I say DOMF up of Z for B, C, F, and G. So if I look at B, C, F, and G, B, C, F, and G, these are the children in the dominator tree. So I look at all the children in the dominator tree, which is B, C, F, and G. And if I look at their dominance frontiers, then their dominance frontiers are pretty large. But which of these are passed up, which means which of them are not strictly dominated by the parent, which is A, and that actually also turns out to be an empty set. And so the final answer is empty set, because A pretty much strictly dominates everything. So anything that is in the dominance frontier of B, C, F, and G will be strictly dominated by A, and so the dominance frontier of A is the empty set. Let's look at dominance frontier of B using this formula. The dominance frontier of B is whatever is the dominance frontier local. So in this case, that's the empty set, because the only outgoing edge is D, but D is strictly dominated by B, so D is not in the dominance frontier of B. So that's the empty set. Union, whatever is in the dominance frontier of D and is passed up to B. So in other words, whatever is in the dominance frontier of D and is not strictly dominated by B. What is in the dominance frontier of D? Recall that the dominance frontier of D is B, F and G. And which of these are not strictly dominated by B? Well, all of them are not strictly dominated by B. And so that becomes FGB. And that becomes my final answer. So the idea behind this this statement or this theorem that dom f x is equal to dom f local x union dom f up z for all children z of x in the dominator tree, either the node in the dominance frontier will be an immediate successor, not strictly dominated, or is passed up from a node immediately dominated by x children. And this is, if I think about it from my naive algorithm point of view, then when I do a DFS starting from x, I do a depth first search starting from x, either I find the dominator frontier node right in my first step itself, which is my immediate successors, or I do a DFS on my children of the dominator tree, and whatever I get there, I check whether the answers, whether I dominate any of them or strictly dominate any of them or not. And if I don't strictly dominate them, then they become a part of my dominance frontier. So either the node will be an immediate successor, not strictly dominated for it to be in the dominance frontier, or passed up from a node I dominated by X, one of the children in the dominator tree. So my final algorithm looks like the following. I'm going to do a bottom-up traversal of the dominator tree for each node X in a bottom-up traversal of the dominator tree. So this is the dominator tree. You compute the dominance frontier in this order of each node X. For example, I'll first compute the dominance frontier of D, then I'll compute the dominance frontier of E, and then I will see which of the nodes in the dominance frontier of D pass up to B. Plus, when I do that, I'm also going to consider the DF local, the dom F local of B. Similarly, I'm going to pass up the dominance frontier of E to C and see which of those actually pass up. Plus, I'm going to look at the local dominance frontier, which is the immediate successors of C. And so that's how I'm going to share the work that I'm doing for different nodes. So for each X in a bottom-up traversal of a dominator tree, initialize the dominance frontier DF to the empty set. For each Y belonging to the successor of X, which in the control flow graph, this successor relation is based on the control flow graph. If idom Y is not equal to X, so if the immediate dominator of my successor is not X, if the immediate dominator of X's successor is not X itself, that basically means that X is not, Y is not strictly dominated by X. Because if Y was strictly dominated by X, then idom Y would have been equal to X. Because after all, Y is the successor of X in the control flow graph. And then we basically add Y to the dominance frontier. This is the local part of the dominance frontier computation. Otherwise, I iterate over all the children of X in the dominator tree. And for each child, I look at its dominance frontier. So let's say the child is Z. So for each child, I look at the dominance frontier and I see which of them pass up to X. And to check which of them pass up, I again check whether the immediate dominator of Y is X or not. So once again, X will strictly dominate Y if and only if Y's immediate dominator is X, because Y is in the dominance frontier of a child of X. Checking whether Y is strictly dominated by X or not is equivalent to checking whether the immediate dominator of Y is equal to X or not. And so if immediate dominator of Y is not equal to X, then I add Y to the dominance frontier of X. So this is the algorithm to compute the dominance frontiers in a single bottom-up pass. And compared to the naive algorithm, we are reusing the work. So for example, we are reusing the effort that we spent for computing the dominance frontier of D in computing the dominance frontier of B, and from there in computing the dominance frontier of A, and so on. And because of that, we can get better running times than the quadratic running time. How much better we can get? Well, let's analyze the running complexity. So we are, for each node X in the graph, in bottom-up traversal, but doesn't matter, we're going to look at each node, and we are going to look at all the outgoing edges of that node. So for each node, we look at all the outgoing edges exactly once in this step. So that basically means that each edge is looked at exactly once. So this statement here, the check here is going to be executed at least order E times. So that's order E. And this statement here is executed for all the children of every node X. But recall that because this is a tree, if I sum up of all the children, then that's just the number of nodes in the graph for every node X. And for each child, I iterate over all the dominance frontiers of that child. So that basically means that if there are, if for a node X, I look at every node X and I do, the amount of work that I do is basically the size of the dominance frontier of X, because that's the number of times this inner loop is going to iterate. So the total amount of work that I do is summation over X, which X represents the nodes in the graph, size of dfx, so mod dfx, and that basically represents the amount of work that I'm doing at this step here in DOM F up. So overall, because of these two steps, df local and df up, the total amount of work that's being done in this algorithm is order E plus summation dfx over all the nodes x. Now we know that if order E is basically linear in the size of the graphs, but how big is summation dfx? Well, in a good case, this could be linear as well, because assuming that all the dominance frontiers are small, let's say constant sized. But if dfx could be larger, and how large can it be? The dominance frontier of a node can be as large as the size of the number of nodes in the graph, in which case this could potentially become quadratic. But we are going to characterize this in more depth and detail in the subsequent modules.